of very plausible situations where there is no Condorcet winner, in which case then this method is not going to take us very far. What are the consequences? Of course, we know Arrow's theorem. Okay, Condorcet winner is the case where the domain of preferences is restricted, so voters kind of agree that A is better than everything else. And that's the situation we have. So one interesting situation where the Condorcet winner can be applied fruitfully is the following silly example, but that does have a number of natural explanations. Suppose there's a town, and the town is going to be served as a long, narrow town, with one street and all the houses along the street, and this new bus line is going to go through the town, and there's going to have one stop. And the road is very long, so there's people living in number 1, people living in number 2, 3, 4, etc. And the last person along the town is at the extreme periphery and is the last person. So the bus comes that way, and obviously on the way back. Yeah. The question is, where do we put the stop? Now, every citizen in this town would like to have the stop opposite their house, because then they can just walk out of the house, go brush their teeth, see the bus coming, finish brushing their teeth, and jump on the bus and go to work without having to wait for the bus under the rain, etc. So each of them has a preferred location, but they also have a second preferred location, a third preferred location. So if you live in 4, if your address is number 4 Main Street, then you want the bus at number 4. But then you said, well, suppose I can't have it at number 4, what's my second preferred location? Well, I have 2, one is number 3 and number 5, because then I go out, I have to wear a short route. So if everybody's like that, and they prefer the bus stop in front of their house, then it's easy to show, because of the median theorem, that there is a Condorcet winner in this case. So any two locations, you take any two locations, and there's always a location that wins every binary choice that involves it. And this location is the one right in the middle. Okay? Why? Well, suppose there are, so if n is odd, but then if n is even, then it goes up the two. Suppose n is odd, so n is, say, 101. Okay? Now, if you live at, so people live at 1, 2, 3, 4, so the median is 51. So suppose now we vote between 1 and 2. Okay? Who's going to win between 1 and 2? 2. Why? Because the only person that's going to vote for 1 is 1, and all the other people will vote for 2. Okay? And who's going to win between 40 and 41? 40. Sorry? 41. Why? Because the people from 1 to 40 are going to vote 40, and the people from 41 to 101, of which there are 61, they're all going to vote for 41. Okay? So the nearest you are to the median, the more votes you get. But when you are exactly at the median, so who's going to vote between 51 and 50? Okay, who's going to win between 51 and 50? There's 50 people voting for 50, and 51 people voted for 51. What about between 51 and 52? Again, 51 vote for 51, and 50 vote for 52. What about 51 and 7?
7 people voted.
A bit more than 7.
That's still less than 51.
Sorry?
But
There's still less, because all the people between 58, 39, 29, all the people between 1 and 29 vote for 7, all the people between 30 and 101 vote for 51. Okay, so 51 is the Condorcet winner. It's going to beat every voter. every other option, and the reason is because we can apply. You okay? Yeah. You can apply the so-called median voter theorem. Have you heard about it?
Yes.
Yeah. Okay. What does it say? It says that. Now you have to be careful here because you probably heard. I don't know who's taught you the median theorem, the median voter theorem, but it's often taught in the wrong way. And the correct way to do it, and I'm going to give an example of a paper where it is explained correctly, is the following. If there is a number of policy choices which are unidimensional, okay, so my bus line is unidimensional, we got a road, you have to decide the bus stop. So if the choice is unidimensional, and if there is a way to order the individual preferences in such a way that every voter has preferences that are single-peaked, with a single-peaked, then there's a best alternative, and that is there's a best alternative, and there's only one preferred point. Okay, one preferred point in the sense that there isn't one local maximum. Let me call it that way. Okay, so if every voter has a single local maximum in their preferences, and for the same ordering of the choices. Okay, notice here I'm ordering the bus stops in the natural way to do it. Okay, so I begin with 1, 2, 3, etc. But I don't have to do that. Okay. Maybe I don't know if you know what the numbering is like in Venice. Road numbers in Venice are crazy. House numbers in Venice are crazy because they're not by road, but they are by area. So voters would have a preference which is, or prefer the number 65, then a number 2011, then a number 82, then a number 712, and so on. Okay? But if there is a way that all voters agree, and every voter has a single local maximum, then we are in the situation where we can apply the median voter theorem. Okay? So in this case here, there are 3 voters. The choices are ordered along this way. And so, for the same ordering of voters, this voter 3 has this local maximum, voter 2 has this local maximum, and voter 1 has that local maximum. So if all voters have a single local maximum, then we are in a condition where the median voter theorem applies. In this case here, for this ordering here, we can see that this voter U has 2 local maxima, 1 and 2, and this voter here has 2 local maxima, 1 and 2. Okay? Now, so this ordering is no good. Okay? But I could change the order refined, as we will see in the specific paper, a local maximum. So, however, if for every ordering, I'm in this situation where at least one voter has more than one local maximum, then preferences are not single peaked. Okay? And this is the theorem. Okay? So if there is an odd number of voters, this can be relaxed in some simple way, and the policy space is one-dimensional. If all voters have single peak preferences, then the median of the distribution of the voter preferred option is a Condorcet winner, just like our bus stop along the route. And so there will be aggregation, and that's known as the Otterling's principle of minimal differentiation. It's probably now, yes, probably it's now a good time to stop. So we're going to, any questions? Yes.
Two questions. The first one is trivial. According to you, does the in politics normally there is this the paradox, not the paradox. This theorem is synthesized by the two ice cream sellers that are on a beach and just to have more customers, they arrive to the center.
Yeah.
Does this apply?
Now that is this is the principle of voting split minimum. So that's an IO problem, not voting problem. So the question is, where would firms choose to locate their product in the product space?
But in that case,
So
it's
just-
for politics.
Yeah.
Just like you send that the slide when you suggest center party will win.
Yes. So in a sense it's similar because you want. So this is a medium voter theorem that says if there is a ranked ordering of policy choices such that every voter has a single peak, so one single local maximum, then there is a Condorcet winner. Which one is that? Is the median of the distribution of voters along that way. And the median has an interesting property that minimizes the total distance of voters from the option chosen. Okay? And that's why it's called the Hoteling's principle of minimal differentiation. Now, this principle has other applications, one of which is the one he talked about, which is in IO, where will firms choose, and they will choose a point that minimizes the total travel distance by consumers that need to go and get the ice cream along the beach, etc. So they are mathematically they're related, and socially they're also related because you want to minimize the cost. Okay, for in the IO setup is the cost of traveling, in the voting setup is the cost of having your non-preferred alternative. So different forces will lead to the same minimization of cost. So it's an application of that. Do you have another?
Yes, but they're gonna hate me. Just one very fast question. Does this relate with the Aaron possibility theorem? I mean, when we don't have single peak preferences, we don't have a first preference.
Well, Aaron possibility theory is more general than that, which says that for some special, here I'm restricting the domain. If I restrict the domain, in the sense that I require that voters have a single peak, then I have a good choice that satisfies all the other principles, satisfy the relevant. If I add another house here, well, no, it's not preferred by any. Well, it is preferred by somebody. So suppose I add the house here, so there is a completely irrelevant alternative, but this lies, and that's not going to change that. Satisfy the Pareto dominance, there isn't anything but dominance, and the non-dictatorial choice, because there isn't a single voter if I change choice. So, but it restricts the domain. And what Arrow's theorem says that if you change the voting, then somebody else is going to collapse. So it is related. So there are Arrow says that there are situations where a single social choice can be made, but not all of them. There will be some where you can't. So that's the... Any more questions? If not, I'll see you tomorrow, hopefully at the right time, which is
2.
Tomorrow,